has achieved tremendous commercial success as premium displays. The examples include smartphones such as Galaxy, iPhone, and OLED TV, and early-stage wearable electronics such as smartwatches and VR displays. And OLED is expected in the future to be adopted in high-resolution VR/AR gears, automotive displays, as well as free form factor phones. However, the biggest problem that may potentially prevent the further success of OLED display is burn-in. Burn-in is a stain-like feature that is sometimes observed in overly used OLED displays. Burn-in is caused by short OLED lifetime and certain use cases. The use cases that worsen burn-in include static content, high temperature, and high brightness. The static content includes channel logo, menu bar, icons, and so forth. High temperature is easily met in outdoor use and due to poor heat dissipation. High brightness is required in outdoor use as well, and the highlight for HDR features and for the personal preference. On the right side of the table shows OLED products at risk due to these use cases. TV, phone, watch, and automotive displays use lots of static content, and thus they are at a high risk from burn-in. However, the first three are at a relatively low or moderate risk against high temperature and brightness compared to the next two applications. VR display suffers from high temperature due to poor heat dissipation. This is because the VR gear cannot be overloaded with a high-performance fan to minimize its mass and volume. Further, VR display requires to produce very high brightness because of poor efficiency of the embedded optics as well as HDR operation. Because of these reasons, VR displays are highly subject to burn-in. The most harmful factor for the automotive displays is high temperature. The reason is because the temperature inside the car during the sunny day in summer can easily go above 80 degrees C, which is far beyond the normal operating temperature. Thus, burn-in in many OLED applications need attention and should be properly treated. Before we go further into the topic, let's define important terminologies related to OLED lifetime. Burn-in is discoloration of areas on the panel caused by cumulative and non-uniform use of the OLED pixels. This condition can be easily met by static content that are fixed in position on the panel at a constant brightness and is used for a longer time compared to the other pixels. OLED degradation means performance of OLED permanently degrades over time, usually under constant current density J. OLED degradation has two aspects, the luminance drop and voltage rise as a function of time of operation. In fact, the voltage rise is not much a big concern from productive perspective because OLED circuit is current driven. So long as delta V is contained within the secured voltage headroom, constant current keeps flowing across the OLED. However, please note that the too high delta V may disrupt pixel circuit operation. And delta V actually includes very important information on degradation, which will be discussed later in the greater detail. OLED lifetime means the time that elapses until initial luminance at constant J reduces to the certain threshold value. For example, T80 is elapsed time until luminance decreases to 80% of its initial value at a given J. The lifetime threshold depends on the type of products. Display uses T95 or T97. However, lighting uses less stringent threshold of T70. Then the question is why different lifetime threshold is used for OLED display and lighting differently. The reason is because of difference in their configuration for the comprising OLED devices. The phone is comprised of repeated units of RGB pixel, while lighting consists of single or multiple white planes. The phone uses dynamic content such that brightness and color of the individual pixel is dynamically changed over time. On the other hand, the lighting uses uniform patterns. Due to this, degradation of the phone panel is differential, meaning individual pixel degrades differently compared to the other, while the lighting panel degrades uniformly and globally. Because of this, the phone generates the burn-in features with mid to high spatial frequency, which is highly visible to the eye. However, the lighting generates global and uniform burn-in feature, which less stands out. Therefore, the phone requires a stringent LT threshold of T95 for individual RGB pixel to generate visual artifact, while the lighting uses T70. However, threshold for lighting should consider color shift as well. The reason is because white OLED used in the lighting is strongly subject to color shift as a function of degradation time. Thus, LT threshold for lighting should consider not only the luminance degradation, but also color performance degradation. Let's switch gears and discuss required luminance level depending on the products, which will determine the aspect of OLED degradation and burn-in. The latest smartphone with an HDR feature is able to produce about 1200 candela per meter square, or nit. In fact, the phone uses the anti-reflective coating to minimize the reflection of the ambient light and thus to enhance outdoor visibility. However, unfortunately, it also cuts luminance from the OLED panel by half. So, the luminance before AR coating should be 2400 nit. Now, if we assume the fill factor of the pixel is about 30%, the pixel level luminance for the phone should be 8000 nit. Now, let's compare this with the VR OLED display. In the dark headset, 150 nit is sufficient for the eye, which seems quite low. However, the thing is not as simple as it sounds. Simply speaking, there are two major components for VR display module, the magnifying lens and micro display to provide the visual stimuli as shown on the left bottom figure. In order to achieve large field of view, a high diopter lens is needed. At the same time, to reduce the volume and to avoid optical artifacts, lots of components should be compressed in the lens. So, the lens has unavoidably low optical efficiency, about 10%. In the meantime, micro OLED display should operate at 25% duty cycle to avoid motion blur and judder as shown on the bottom right figure. 25% duty cycle means that pixels only turn on during a quarter of refresh time, so that effectively increases the frame-to-frame time and reduces the lagging. This is good and bad. The good side is that your pixels are used for only quarter of actual time. The bad side is that 4 times higher luminance should be concentrated to provide same luminance stimuli to our eyes. Based on this information, let's calculate luminance requirement for VR displays. 150 nit is required at product level, but considering the big loss by lens, the luminance before lens should be 1500 nit. If pixel fill factor and duty cycle are considered, pixel level brightness should be 20,000 nit, nearly 3 times higher than the phone requires. How long the lifetime is good enough for the products? A good rule of thumb for lifetime requirement is that T95 over 200 hours at maximum luminance for more than 2 years of product life. This is possible because the users do not use the products at maximum brightness all the time, but about 30% of it on average, and for less than 6 hours per day. Also, the burn-in compensation extends further the product life that will be shown in the next slide. Suppose that the phone OLED achieves T95 of 200 hours at max luminance and it is sufficient. However, problems arise under accelerated aging condition as in the VR OLED displays. Higher luminance leads to shorter OLED lifetime, and as explained, VR OLED requires 3 times higher luminance than phone OLED. Based on empirical relationship, this leads to 10 times shorter lifetime. So even after considering 25% duty cycle stretching the lifetime by 4 times, lifetime of VR OLED may be still 3 times shorter than phone OLED. So OLED devices good enough for the phone will not be appropriate for VR displays. What about temperature? Usually, every 10 degrees C increase leads to more than 2 times lifetime reduction. VR display is confined within the headset, and because of high computation power and difficulties in cooling, temperature of the VR display can easily go above 40 degrees C. Automotive displays may be even worse. Without cooling, temperature inside a car during the summer day can easily reach 80 degrees C. Under these harsh operating conditions, OLEDs will degrade at much faster rate than those in the phone at room temperature. So the take-home message is OLED sufficient for the phones may not be necessarily good enough for the other products. A short lifetime is manifested as burn-in and it needs to be properly treated. The well-known method is downward normalization, where you level down the luminance of the entire pixels to match the most degraded one. In other words, the relatively fresh pixels should give up some luminance due to the degraded pixels. The result is that the burn-in features are removed, but the overall panel becomes dimmer. However, this strategy effectively works because human eyes are more sensitive to burn-in features with some spatial frequency than overall luminance reduction. To apply this compensation, it is important to record pixel use history in memory, at what luminance pixels were used, for how long, and at what temperature. Also, we need a predefined lifetime model that predicts how pixels degrade under this recorded condition. By feeding this information into the algorithm, you can update pixel values after compensation. While history recording is easy, having a well-defined lifetime prediction model is challenging, yet very important. A well-known model for luminous degradation is stretch exponential decay fit, or SID. It is based on Weibull distribution, assuming random failure of millions of excitons in the devices. SID provides a fairly good fit for different devices and for different brightnesses as shown on the top right figure. Thus, an empirical model, including SID and Arrhenius equation accounting for the temperature dependence, fits universally well to various data and statistically validated. However, the drawback is that the fit is based on randomness, and therefore it is hard to find any physical meaning from the parameters. Therefore, unless the device set is finalized for production and supported by lots of measurements, such empirical modeling is not useful. In this sense, we need to introduce the physics-based model to understand what is happening in the devices and eventually evolve it to the predictive model to estimate lifetime even without measuring it. That is a very ambitious goal, but really needed to move forward. Section 2, Phosphorescent OLED Degradation and Defect Analysis. Degradation factors that affect OLED lifetime are divided into extrinsic and intrinsic factors. Extrinsic factor is the process-dependent contaminant introduced in OLEDs. These include residual water molecules and organic impurities in the process chambers. Such extrinsic factor can be controlled well by reduced fabrication time and occasional maintenance of the fabrication system. Also, by employing thin film encapsulation, further intrusion of extrinsic impurities into the devices can be effectively prevented. The intrinsic factor is interactions of the excited states in OLEDs, which causes a complicated lifetime problem. As its name implies, the intrinsic factor is hard to be removed and varies from device to device, which complicates the analysis. The excited states in OLEDs include positive and negative polarons, and singlet and triplet excitons, as well as the most critical factor, the hot excited states. The hot excited states are generated by bimolecular annihilations. Here, bimolecular annihilation is the process described as follows. One excited state transfers its energy to the other and relaxes to the ground state non-radiatively. Then, the other state is highly excited with nearly doubled amount of energy, and such state is referred to as the hot excited state. Hot excited states are known to be a main cause of device degradation. The figure on the right shows the schematic of triplet polaron annihilation, or TPA, that can potentially happen in the phosphorescent OLEDs. Triplet exciton transfers its energy to the neighboring positive or negative polaron and non-radiatively relaxes to the ground state. As a result, the electron is promoted from LUMO to the LUMO plus N in negative polaron, or to the HOMO from the deep level HOMO minus M in the positive polaron geometry. The former and later cases are referred to as hot negative or positive polarons, respectively. Such highly excited polarons with high energy have potential to dissociate the molecules, leading to OLED degradation. Bimolecular annihilations in phosphorescent OLEDs include TPA and triplet-triplet annihilation, or TTA. In fluorescent OLEDs, we have singlet-triplet annihilation, or STA, as well as TTA and TPA. Here, fluorescent OLEDs include all types such as triplet-triplet fusion, TADF, and hyperfluorescent OLEDs. The figure on the left is a Jablonski diagram describing TTA in phosphorescent OLED, or PHOLED. As similar to TPA, highly excited exciton is generated as a result of annihilation between two triplets. In fact, most of the hot excitons are relaxed back to the original first exciton level. However, some of them, saying 1 out of 10 to 22 excitons, are coupled to the pre-dissociation potential or dissociation limit. Once coupled to these unbound states, the interatomic distance keeps increasing and eventually the molecule is dissociated. As a result, The fragmented species, or defects, remain in the device and act as permanent degradation centers. They trap charges leading to the voltage rise and serve as the centers of trap-assisted recombination and direct exciton quenching, leading to the luminous drop. Now, let's see how defects affect the device performance. During device operation, some of excitons and charges undergo annihilation with each other, creating hot excited states. A few of hot excited states dissociate the molecules and leave behind the defects. Interestingly, if you measure the mass spectra of the aged devices, you will find the defects not only in the emission layer, or EML, but also in the other layers such as Hole transport layer, or HTL, and electron transport layer, or ETL. Many researchers, including myself, have claimed that the degradation of the EML is caused by TTA and TPA. Some believe that the sole excitons or polarons themselves are the cause. Degradation mechanism of the HTL and ETL is still unclear. One possibility is the TPA at the interface between the EML and HTL, and that between EML and ETL. The participating species in this case are triplet excitons in the EML and polarons in the transport layers. Or another possibility is polaron itself that flows through the transport layer and leads to the degradation. However, these are yet hypothetical, and therefore more study is needed to identify the degradation mechanism of the transport layers. Now, since luminous drop is mainly associated with the excitons, it is only affected by the defects within the EML. Such EML defects quench excitons or act as Shockley Reed Hall recombination centers, leading to the non-radiative loss of the excited states. On the other hand, the voltage rise can be induced by charge trapping by the defects in all OLED layers. Therefore, voltage rise involves quite complicated information about the device degradation and thus worth being investigated. In addition, we should pay greater attention to the EML defects because they affect both luminous drop and voltage rise, so that they are key to understanding device degradation. Before we move deeper into the topic, let's briefly review how trap-assisted or Shockley-Reed Hall recombination occurs and how they affect the OLED performance. Let's take the electron trap for example. The electron traps have the energy level E sub t situated above the Fermi level E sub f. Thus, such states are likely to be empty of the electrons and energetically favorable to capture the free electrons in the LUMO level. If the trap energy is sufficiently far from the LUMO level, it is called the deep trap. If the trap is situated only a few kT, the thermal energy below the LUMO level, it is called the shallow trap. The Shockley-Reed Hall, or SRH recombination, occurs between the trapped electron and free hole in the HOMO level, or between the trapped hole and free electron in the LUMO level in case of the hole traps. A likelihood of charge trapping and concomitant SRH recombination is high for the deep traps compared to the shallow ones. In fact, even though the charges are trapped by the shallow traps, they are easily released back to the original level by the thermal energy. So, the SRH recombination more likely occurs through the deep traps rather than the shallow ones. Once occurs, The SRH recombination deteriorates electrical and optical performance of the device for two reasons. At a given current density, the trapped charges increase the electric field within the device and thus the voltage across it. This indicates the increased resistivity of the device. Secondly, the following SRH recombination is usually non-radiative. This means that free charges get lost even before forming the excitons, leading to the optical loss. In short, this SRH recombination, along with the exciton quenching, is the major mechanism of luminance loss by the defects. Interestingly, the traps affect the electrical characteristics of the device differently depending on their energy levels and positions. If the energy level of the traps becomes deeper relative to the charge transport level, the device becomes more resistive at a given current density. If the location of the traps are closer to the charge injection electrode, the device becomes also more resistive. The detailed analysis on these observations will be shown in my invited talk in session 69, OLED Devices 4. Coming back to the main discussion, let's talk about the classification of the EML defects. If you do the mass spectroscopy to the aged device, the EML molecules generate various types of defects. They are simply categorized into two types in my analysis. One type is the fragmented species, which have the smaller molecular mass than the original molecules. Interestingly, the other type, having a larger molecular mass, is also found, and these are created by the radical reaction between fragment and fragment, or fragment and original molecules. These fused species have longer conjugation, and thus they form the defects with a smaller energy gap than the original molecules. This type of defects is denoted as type A. Likewise, the fragmented species have a shorter conjugation, leading to the defects with a larger energy gap than the original ones. This type of defects is denoted as type B. This classification based on the molecular mass and energetics can be generally applicable to any material and device systems. A particle in a box in quantum mechanics may be one of the easiest ways to describe the relationship between the energy level and the conjugation length of the molecule. In the model, the electron is assumed to be confined in a box of length L with infinite energy barriers and zero potential within the box as shown on the top right figure. Then, a solution to this time-independent Schrödinger's equation represents the wave function of the electron in the box. The wave function, denoted as psi sub n, is an eigenfunction for the Hamiltonian operator and has a corresponding eigenvalue denoted as E sub n. This E sub n, varying with the integer n, denotes the discretized energy level that the electron in a box can possibly occupy. Please note that the energy of this electron is inversely proportional to the square of L, the length of the box. This model can be roughly applied to the molecule. In such a case, the length of the box L is the conjugation length, which indicates the physical space that the electrons are confined within the molecule. Thus, the longer the conjugation length is, the smaller the energy gap of the molecule becomes. In the same vein, the shorter conjugation length of the molecule leads to the larger energy gap. Let's first discuss about type A defects how they act in the device. As a reminder, the type A is a large molecular mass defect with a long conjugation and thus a small energy gap. They may form the deep hole or electron traps, and trapped charges in them recombine non-radiatively with the opposite free charges. Or the electron and hole can be trapped together by these defects, and the resulting exciton non-radiatively decays. These reactions 1 and 2 represent the Shockley-Rittal recombination. In addition, excitons transferred from the host or the dopant to the empty defects can be directly quenched. All of these non-radiative reactions are possible because the CT or direct excitons on the defect have smaller energy than that of the dopant. In summary, what the type A defects do in the EML are charge trapping leading to the voltage rise and serving as the centers of SRH recombination and exciton quenching leading to the luminous drop. Now, let's take a look at the type B, the small mass defects. They have short conjugation and therefore likely have a larger energy gap with some exceptions. They may form shallow traps so that even though they trap charges and form CT or direct excitons, those are transferred to the dopant and subsequently participating in radiative recombination. This is possible because the type B defects have a higher exciton energy than the blue dopant. So what they do in the EML is that they still capture charges leading to the voltage rise, but excitons on these type B defects return to the dopant so that they do not affect luminous degradation at all. In summary, the EML defects are categorized into type A and type B based on their molecular mass. The difference is that type A has the smaller energy than the dopant and excitons can be lost on them. On the other hand, type B has the larger energy than the dopant so that excitons can be potentially returned to the dopants. If the type B defects are adjacent to the type A, excitons can transfer from B to A, leading to the non-radiative loss as well. Based on understanding so far, we can develop the Follett degradation model. This work was conducted by the instructor when worked in the lab led by Professor Stephen Forrest at the University of Michigan. These are coupled rate equations for electrons, holes, and excitons denoted as small n, small p, and capital N respectively. Also, here are the rate equations for the type A and type B defects denoted as Q sub A and Q sub B as shown on the top right. These 5 equations are numerically solved to yield excitons and defect densities to fit data of luminous degradation and voltage rise as shown in the bottom right. There are a few things to note here. The hypothetical scenarios that we described about the defects are reflected in these rate equations. Also, in these rate equations for the defects, we assume that the type A and B defects are generated by TTA at their own rates. There has been an ongoing debate on degradation mechanism among TTA, TPA, exciton, or polarant itself. However, my answer is that everything is possible and it may be dependent on the device structure. We chose the device system that fits best with the TTA mechanism as will be shown in the later slides. Lastly, the voltage rise is induced by charge trapping by type A and B defects in the EML, and all the other defects outside the EML denoted as Q sub ext. By using the lifetime model, we fit data for 3 different device systems, one with uniformly doped EML, the other with graded EML, and the tandem device as shown on the top left. These are blue phosphorescent OLEDs whose EML consists of MCBP and iridium DMP3 as the host and the dopant respectively. As you can see, our model provides a good fit for both luminous degradation and voltage rise for all 3 device systems. Our model claims that the luminous degradation is caused by SRH recombination and exciton quenching solely by the low energy type A defects. On the other hand, the voltage rise can arise due to the charge trapping by all the EML defects type A and type B, as well as the external defects outside the EML. From the model fit, we can analyze how the defects affect the device performance. The graph on the top right shows lifetime data of the uniformly doped EML device given as the red circles and a model fit in solid line. The data was measured until T50, which is about 500 hours. The bottom graph shows a ratio of defect formation per molecular sites for Q sub A, Q sub B, and Q sub ext. These are obtained from the above data. Interestingly, even after 500 hours of degradation, total defect ratio is only about 0.03%. This means that only 0.03% increase of defects can lead to more than 50% luminance reduction in the device. Further, such luminance reduction is resulted 90% from SRH recombination and 10% from direct exciton quenching. This indicates that a majority of charges get lost due to the traps even before forming the excitons. Another learning is that a sharp initial rise of voltage rise is caused by the external defects, and a long-term steady increase is due to the EML defects. There has been a follow-up work to detect the defects in the aged devices and identify their energetic characteristics. The fresh and aged devices until T80, T60, and T40 were analyzed by a mass spectroscopy. The mass peaks newly arising in the aged devices were assigned to the defects, and a time evolution of their densities was tracked as shown in the bottom left figures. As expected, the density of the defects increases with degradation time, consistent with the physical model. In addition, the molecular structures of the defects were reconstructed based on their mass peaks. With the reconstructed structures of the defects, their HOMO, LUMO, and exciton energies were calculated. As shown on the right figure, some defects have the lower HOMO-LUMO gap and thus the triplet energy than the dopants, so they can be classified as the type A defects. On the other hand, some larger energy gap defects are found which may act as the shallow traps but are optically inactive due to the higher triplet energies than the dopant. Such defects can be grouped as the type B defects. Therefore, this follow-up study supports the modeling work in that it experimentally shows the density of the defects increases with the aging time and classified the defects into 2 groups based on their energetics. This section will be closed after discussing this recent modeling work conducted by the Professor Jang-Joo Kim's group at Seoul National University. In this paper, the researchers claim that the EML defects are generated by the unstable dopant polarons, and the external defects outside the EML are created by the exciton-mediated processes as shown in the right figure. Based on this assumption, they fit the lifetime data for the blue phosphorescent OLEDs as shown on the left side. Another key feature they introduced in the model is the process-dependent impurity. It is assumed that water, oxygen, and organic impurities were initially introduced in the device with a certain density. And such impurity is activated by a polaron and turns into the defect. As the time increases, the density of these defects is saturated. In the model, these impurity defects were responsible for a rapid initial rise of voltage as shown in the first and third figure on the left side. The implication of this work is as follows. The researchers showed that the degradation mechanism can be manifold. In this work, the polaron was a major factor. But depending on the device system, it could be a combination of many processes, including polaron, exciton itself, and exciton-mediated reactions. Section 3, Recombination Zone. Recombination zone means a spatial distribution of the excitons, or in other words, a density of the excitons as a function of position in the EML. Before forming the exciton, the electron and hole are attracted to each other by coulombic force. Then, the electron and the hole are held together with a certain binding energy, becoming an exciton. Such process of exciton formation is called Langevin recombination. The detailed explanation on exciton properties will be given elsewhere. We can infer that the spatial profiles of the electrons and holes determine that of the exciton. Thus, depending on the relative injection and transport of charges in the EML, we can expect three cases. Let's assume that the EML is sandwiched by good electron and hole blocking layers. First, if the hole is much faster than the electron, the exciton will be piled up at the hole blocking interface. The second one is the opposite case, where the electron is faster than the hole. The third case is that the exciton is uniformly distributed across the EML due to the well-balanced electrons and holes. The last case is optimal for high-performance OLEDs, as will be explained in the next slide. A recombination zone, or the spatial profile of the excitons, critically affects the efficiency and lifetime of the device. A uniform recombination zone leads to a high efficiency and long lifetime, as demonstrated by two works shown below. The major reason for that is because with the uniform recombination zone, the bimolecular annihilations and thus the defect formation more uniformly occur. This is proven beneficial both in efficiency and lifetime of the device. The first work in the bottom left figure compares three different EML structures. The first one is a double or bilayer EML. The second one is a mixed EML where electron and hole transport hosts and the dopant are mixed at a constant concentration. The third one is degraded EML, where the hole transport and electron transport hosts are graded at high to low concentration in opposite directions across the very thick EML. As the EML structure progresses, the recombination zone becomes more uniform and broad. As a result, the device with more uniform recombination zone exhibits the higher efficiency. The second work in the bottom right figure shows the recombination zones in the EML of 3 blue devices. As the exciton profile becomes relatively more uniform from D1 to D3, the device lifetime is progressively more enhanced. From these two works, we can infer that by avoiding locally concentrated bimolecular annihilations by having a uniform recombination zone, the high efficiency and lifetime can be achieved. And the key to achieving a uniform recombination zone is to make electrons and holes balanced in the EML. Then the question is how to measure the recombination zone. One of the easiest ways is the sensing layer method. The procedure of this method is as follows. You have to insert a thin layer with the low energy dopants at a position of interest in the EML. Then, nearby excitons within the sensing zone are transferred to the sensing layer. Such excitons in a sensing layer should emit in different color compared to the excitons in the rest of the EML. Thus, to serve these two purposes, red dopants are preferred as the sensing layer. The width of sensing zone is determined by the exciton transfer radius between the EML and sensing dopants, which will be discussed later. Now, exciton density from the sensing layer can be spectrally extracted from the device spectrum. The figure on the bottom left shows the EL spectra of the blue follets without and with the sensing layer. The device with the sensing layer has reduced blue intensity because a certain portion of the EML excitons are transferred to the sensing layer. Thus, a relative ratio of the excitons in the sensing layer versus those in the entire EML can be translated into the local exciton density at the sensing position. The way to calculate the number of excitons from the spectrum is quite straightforward. You have to simply divide the spectral intensity at a given wavelength by the corresponding photon energy, which yields the number of excitons per second. Then you can integrate that to obtain a total number of excitons per second within a designated spectral region. If we assume the number of excitons in the device with and without the sensing layer is same, we can obtain the relative exciton density in the sensing layer by using these calculated numbers. Now, from the multiple device spectra with a sensing layer at different positions, we can obtain the local exciton density as a function of position. Such a spatial profile of the exciton density, as shown in the bottom left figure, is referred to as the recombination zone. Please note that only one sensing layer should be inserted per device to obtain the local exciton density. There are several requirements for the sensing layer. First, the energy of the sensing dopants should be smaller than the EML dopants so that their spectra can be well separated with each other. So, the blue OLED can be paired with the green or red sensing dopant and green OLED with the red sensing dopant. However, there's no available sensing dopant in the visible spectrum that can be paired with the red OLEDs. Potentially, the infrared dopants can be used, but their efficiencies are usually very low, and a spectrometer that covers a broader range of the wavelength is required. The second requirement for the sensing layer is that it should be electrically inactive. That is, the device with a sensing layer should be neither more conductive nor more resistive. To serve this purpose, a thin sensing layer less than 2 nanometer with a small concentration less than 2 to 3 volume% is recommended. The third requirement is a narrow sensing zone to maintain high spatial resolution of the profile. A high spatial resolution means an accuracy of the local exciton density. The sensing zone, depicted in the top left figure, is determined by the exciton transfer radius from the EML to the sensing layer. The point is that such transfer radius should be small enough not to attract too much excitons far from the sensing layer. Thus, a small exciton transfer radius is equivalent to a narrow sensing zone, which leads to the relatively accurate local density of the excitons. Let's discuss further the sensing zone, or a spatial resolution of the recombination zone. The process of exciton energy transfer is twofold: the Foster and Dexter transfer. The Foster transfer is a long-range dipole-dipole interaction process. It occurs dominantly between singlet and singlet, and only weakly between singlet and triplet under spatial circumstances. The Dexter transfer is a narrow-ranged charge exchange process which occurs between singlet and singlet or between triplet and triplet. The sensing zone is determined by which energy transfer process is dominant in the sensing device. There are 4 possible combinations for the sensing devices. Let's see the first combination of phosphorescent OLED with phosphorescent sensing dopant. Due to the efficient intersystem crossing in the FOLED dopant, only a few singlet is Foster transferred to the sensing dopant. The triplets, a majority of the excitons, move to the sensing dopant by short-range Dexter transfer. So this combination has the narrow sensing zone. The second combination is the FOLED with the fluorescent sensing dopant on the top right. In this case, triplets from the EML dopant cannot emit in the sensing dopant and get lost. Instead, a few of singlets move to the sensing dopant by a long-range Foster and participate in emission. Thus, this combination leads to a wide sensing zone, resulting in the low spatial resolution of the exciton profile. The third combination is fluorescent OLED with the phosphorescent sensing dopant on the bottom left. In this case, both singlet and triplet from the EML dopant are harvested by the sensing dopant. So the sensing zone may be determined by the mixture of Foster and Dexter transfer distances. The fourth combination is fluorescent OLEDs with the fluorescent sensing dopant on the bottom right. For the same reason as the second combination, only the singlets are harvested by the sensing dopant, leading to the wide sensing zone. This indicates that the fluorescent dopant is not appropriate as a sensing dopant, but the phosphorescent dopant is an only option. The question is whether the fluorescent OLEDs are okay to be sensed. Care must be taken because, as shown in the third combination, the sensing zone is determined by a mixture of long-range singlet and short-range triplet transfer in the fluorescent OLED. Lastly, the sensing layer method cannot be used for the TADF OLEDs. The reasons will be left unexplained as a homework for the listeners. Section 4. Fluorescent OLED efficiency and lifetime. The fluorescent OLEDs have been continuously used as blue pixels of the OLED panels. This trend will go on until the development of the long lifetime blue phosphorescent or TADF OLEDs, which will take some time. Meanwhile, the efficiency and lifetime of blue fluorescent OLEDs have been surprisingly improved even recently. However, we know relatively less of this technology, partly due to the belief that it'll be eventually replaced by other technologies, which may or may not happen. In this sense, it is important to learn how this technology works, what the issue is, and how it can be improved. According to the spin statistics, it is believed that the internal quantum efficiency, or IQE limit, of the fluorescent OLED is only 25% even with 100% charge balance and PL quantum yield. Thus, this IQE leads to the external quantum efficiency, or EQE, of 5% considering 20% outcoupling efficiency, which is a quite normal value for a random orientation of the emitters. However, the fluorescent OLEDs with the EQE over 5% have been continuously developed, which break the spin statistical limit. This is possible due to the delayed generation of the singlets from triplet-triplet annihilation. Depending on spin angular momenta of triplets, TTA can generate three types of hot excited states: the singlet, triplet, and quintet with total spin number of 2. These three hot excited states are generated with a relative ratio of alpha, beta, and gamma, depending on the molecular energy levels. Here, an additional singlet with a ratio of alpha contributes to the delayed fluorescence, increasing the IQE of the fluorescent OLEDs beyond 25%. Let's calculate IQE of TTA-based fluorescent, or TTAF OLEDs. The injected charges in the EML form excitons, where 25% and 75% of them are singlet and triplet respectively. Here, these initial singlet participate in emission, which is referred to as prompt fluorescence. Now, 75% triplets undergo TTA one another. A half of these excitons become hot excited states, and the other half get lost non-radiatively. Here, hot singlet, triplet, and quintet states can be formed with a ratio of alpha, beta, and gamma. Now, after the first TTA, we have singlet excitons with a ratio of 75% divided by 2 times alpha, and these singlet excitons participate in emission as delayed fluorescence. On the other hand, the remaining triplet excitons with a ratio of 75% divided by 2 times beta undergo the second TTA. These processes are repeated until all the excitons are depleted. Then, the efficiency of total delayed fluorescence is ideally a sum of singlet excitons generated after consecutive TTAs. This is an infinite series with a common ratio of beta over 2 and an initial value of 75% times alpha over 2. So, it can be simplified as 75% times alpha over 2 minus beta. Therefore, efficiency of total fluorescence is a sum of those of prompt and delayed emission, which is 25% plus 75% times alpha over 2 minus beta. Now, let's calculate the theoretical IQ limit for 3 different cases. The first case is the normal one with the spin statistics where hot singlet, triplet, and quintet are formed with a ratio of 1 to 3 to 5. Thus, we can substitute alpha of 1 over 9 and beta of 3 over 9 into the formula for the total fluorescent IQE, which yields 30%. The second case assumes that the quintet state is too energetic to be accessed even after the TTA. In such a case, the intermediate state after the TTA is split back into the two triplet excitons. Since the forming ratio of quintet was supposed to be 5/9, we have an additional generation ratio of triplets by 5/9 times 2. Thus, this second case yields 40% IQE. The last case describes that all the hot excitons turn into the singlet excitons. In this case, the IQE becomes 62.5%. This is a maximum theoretical IQE limit for the TTA-F OLEDs, and it can be possibly achieved under energy resonance condition. Energy resonance for TTA-F OLEDs can be achieved by the following energetic condition. The second excited triplet energy level should be higher than twice the first triplet energy level, as well as the first excited singlet level. Secondly, the intermediate state after the TTA has a higher energy than the first excited singlet level. Then, the intermediate state transfers to nowhere but to the singlet level. Such condition has been observed in several materials. Among these, an anthracene-based derivative has been widely used as a host for blue TTA-F OLEDs due to its large energy gap. It has the low energy triplet and thus can harvest triplets from the blue dopant, which otherwise get lost non-radiatively. Then, such triplets on the anthracene hosts undergo TTA and generate the singlet excitons. These delayed generation of singlets contribute to fluorescence, enhancing the overall IQE of the device. So, one can think that so long as we maintain a high rate of TTA, we can maximize the IQE by stimulating delayed fluorescence. In this regard, one can keep increasing the current density to promote the TTA and thus generation of singlets, hopefully leading to a high IQE. However, at high current density, TTA-F OLEDs also exhibit the efficiency roll-off, indicating there is an efficiency limiting factor. The limiting factor has been proposed to be singlet-triplet annihilation, or STA, where singlet is quenched by the triplet. Thus, TTA and STA are competing processes in the TTA-F OLEDs. TTA generates singlets, but STA quenches them. In fact, this STA is known to be a major reason why the electrically pumped organic laser is not realizable. The STA can occur in a various way among the host or the dopants or between them. A trade-off relationship between lifetime and efficiency is a commonly observed phenomenon in TTA-F OLEDs. It is presumably attributed to the competition between TTA and highly energetic STA. The paper introduced here engineered the recombination zone of the blue TTA-F OLEDs by choosing a different combination of HTL and ETL and by having HBL or not. As can be seen in the table, the orders of lifetime and efficiency of these devices are roughly reversed each other. This may attribute to the irregular recombination zones. That is, more slanted profiles shown in the first two are preferable for a higher rate of TTA and thus generation of the singlet excitons. By doing so, the efficiency of the device can be enhanced. However, at the same time, such irregular recombination zone also promotes STA and other exciton-mediated annihilations, decreasing the device lifetime. More study is needed to support this hypothesis. In 2016, a new TADF molecule was reported, which was somewhat different from the conventional TADF. The material, abbreviated as DABNA, contains boron and nitrogen atoms, which exhibit opposite resonance effect. Thus, as shown in the top row, the LUMO is formed on boron and at ortho and para positions to it, whereas the HOMO is formed on the nitrogen atoms and at the meta position to the boron. This leads to the separation of HOMO and LUMO even in the same molecular moiety, enabling the TADF characteristics. On the other hand, the previous TADF molecules were based on the weakly connected donor-acceptor structure where the HOMO and LUMO are separated in the individual moiety. Thus, this DA structure is unstable and easily twisted in the excited state geometry, leading to a large Stokes shift and a wide full-width half maximum of 70 nanometer. On the other hand, this boron TADF is based on a polycyclic aromatic structure on which HOMO and LUMO are formed separately by using multiple resonance effect on the same moiety. Due to the relatively rigid excited state geometry, it exhibits a small Stokes shift and a narrow full-width half maximum of 30 nanometer. In addition, the DABNA produces deep blue color with a CIE value of 0.13, 0.09 in the bottom emitting OLEDs and has a high PLQI over 80% as well as delta E sub ST of 0.2 EV, enabling the TADF. Despite excellent photophysical properties with a new concept, the usefulness of the boron TADF molecule in the long lifetime device is another story. The table compares the figure of merit between boron TADF and pyrene TTAF OLEDs. Due to a merit of TADF, boron device achieves higher EQE and exhibits a decent full-width half maximum of 28 nanometer, which is even narrower than the pyrene TTAF device in deep blue. However, the boron device suffers significantly from EQE roll-off and even 1000 nit is not reachable, and thus the lifetime is not even measurable. This is attributed to very long triplet lifetime of 65 to 94 microseconds for the boron TADF molecule, resulted from the relatively large delta E sub ST of 0.2 EV. Because of this, the device lifetime is extremely short because of the intense triplet-induced annihilations. The worst problem is that the TADF molecule has a higher triplet energy than the TTAF molecule, possibly leading to highly energetic hot excited states. So maybe the boron material, although it is interesting, may not enable long lifetime TADF device. Nevertheless, tempting merits of the boron TADF are very narrow full-width half maximum and high efficiency in deep blue, as well as very stable material structure. Instead of being used in TADF OLED, the boron material has been successfully adopted in TTAF OLEDs. The figure compares the exciton dynamics in 3 different fluorescent systems. The first one is the conventional TTAF OLEDs based on an anthracene host and a pyrene dopant. The triplets in the dopant are dexter transferred to those in the host, subsequently participating in the TTA. Then, singlets are newly generated with some ratio and Foster transferred back to the dopant for emission. This is the only route of additional exciton recycling, and there is no reverse intersystem crossing in pyrene due to large singlet-triplet gap. Thus, the IQE of this system can vary in the range between 30% up to 62.5% as shown in the table. The full width half maximum is around 40 to 60 nanometer in bottom emitting OLEDs, and the device lifetime is fairly good. The second system shows the boron TADF OLED based on the regular host and the boron dopant. The triplets in the dopant reverse intersystem cross to the singlet for emission. In addition, the host triplets can dexter transfer to the dopants and undergo reverse intersystem crossing for singlet generation. Due to this extra exciton recycling, the IQE of this device can be between 30 and up to 100%. The full width half maximum is decently narrow of 20 to 30 nanometer, but as shown previously, its lifetime is unacceptably short. The last system is again the TTA-F OLED, but with the boron material. Here, the boron is no longer used as TADF, but as the regular blue fluorescent dopant. Thus, it works similar to the pyrene dopant. Since the triplet energy of the anthracene host is more favorable, a majority of dopant triplets may transfer to the host. However, some of the triplets have a chance of direct conversion to the singlet via reverse intersystem crossing, additionally contributing to the IQE. Thus, boron TTA-F OLEDs exploit not only TTA but also reverse intersystem crossing for exciton recycling, leading to potentially higher IQE than the normal TTA-F OLEDs. Furthermore, it can take a narrow full width half maximum due to emission from the boron material and exhibits excellent lifetime by reducing the number of triplet excitons in the device. This is a summary of this lecture. In section 1, we introduced important terms and concepts related to the OLED lifetime. The biggest problem in the OLED displays is burn-in, and it is caused by short device lifetime and certain use cases. In section 2, we learned the fundamental degradation mechanism of the phosphorescent OLEDs. Bimolecular annihilations potentially lead to the molecular dissociation and concomitant defect generation. The defects deteriorate electrical and optical performance of the OLEDs, and such effect depends on where they are formed spatially and energetically. In section 3, we reviewed that the uniform recombination zone is needed for high efficiency and lifetime. And uniform recombination zone is achieved by balanced electron and hole transport and injection into the EML. The sensing layer method is only useful for a combination of blue folate and red dopant. In the last section, we discussed the potential efficiency and lifetime limiting factor for TTA fluorescent OLEDs. Until the blue folate with high efficiency and lifetime comes out in the market, the blue fluorescent OLEDs will be dominated, and the boron-based TTA-F OLED is very promising. Lastly, the fluorescent OLEDs suffer from lifetime and efficiency trade-off relationship, which needs to be addressed in the near future. This is the end of the lecture. I acknowledge Professor Stephen Forrest and his lab at the University of Michigan, where I was educated on the OLEDs, and the most topics in this lecture have been developed. Also, I thank my current sponsors, Samsung Display and Samsung Advanced Institute of Technology, who financially support our lab at Seoul National University. Thank you very much for your attention.